welcome to the first lecture of, what is this, the 6th week? I don't quite remember, of the Introduction to Data Science module. So last week we concluded by talking about linear regression. And I apologize, I recorded this on Tuesday, but apparently forgot to post the link until Saturday. So the linear regression notebook lecture is on the video links now. It's also in the video downloads. But it sits a little bit apart from the other lectures from last week. I just had a total slip of the mind and somehow let this one get away until the weekend. And like I mentioned, it's also under video downloads as linear regression. So we concluded the week by discussing linear regression. And of course, linear regression is a regression problem. There are two broad classes of machine learning problems, or supervised machine learning problems: regression and classification. And today, I'm going to discuss classification. And you can see I've just made a new notebook and entitled it Classification, because this lecture I will be live coding. I'm going to be taking it a little bit slower as a result. And this way you can see kind of my thought process, not only in how I approach the problem, but also develop my code. And when I'm done with this notebook, I will post it to the video downloads folder. So that notebook will go in here as well, along with the video itself. So let's get started. As I mentioned, there are two large classes of supervised machine learning problems: classification and regression. So what differentiates these? Well, in classification, we predict categorical labels. In regression, we predict quantitative numerical labels. I have something caught in my throat. The critical difference is that we can't take a difference between categories while the predicted and actual category, while we can take a difference between the predicted and actual numerical values in regression. Excuse me, really apologize. So, what I'm saying here is when we are looking at a regression problem where we predict some quantitative label, we can take a difference between what we predict and what the actual truth is. We can calculate a quantitative error. When we are predicting a category, we can't take a difference between categories. For example, if we are considering, say we're a travel agent and we want to predict what country a customer wants to travel to. And perhaps they actually want to travel to Uruguay, but we predict that they want to travel to Brazil. We can't take a difference in the mathematical sense between Brazil and Uruguay. So we can't quantify the error there. All we can say is that we got the prediction wrong. This is in contrast to if we're predicting home values, as we did in the linear regression lecture, where we can say by how much were we wrong. Was the house $300,000 and we predicted $350,000, or did we predict $500,000? These two predictions are wrong by different amounts. And so this is going to impact how we measure model performance, and we'll talk more about that next in the next lecture on metrics. So this is actually really the major difference. So I'll actually remove the bullet point. This is the main difference. So let's look at what a classification problem looks like. Let's see here. There we go. So, I feel like this is not Iris data set quite the way I want to import this. Oh, evidently it is. Okay. So I'm going to show you the Iris data set, which is a data set containing 150 measurements, or 150 observations, with 4 different features: sepal length, sepal width, petal length, and petal width, measured in centimeters. And each observation is a different type of iris. This is a very famous data set that is actually quite old, nearly 100 years old, used by developed by biologist Ronald Fisher. It's a classic data set for teaching classification and basic statistical ideas. So it's a data set about flowers, and we basically have measurements of the different physical characteristics of this flower. How long and wide are the petals, and I'm not actually familiar with, I guess the sepal is the stalk that the pollen sits on, which I can't even see here. I am not a botanist, so I'm not actually familiar with what these terms necessarily mean. Nonetheless, so I haven't imported pandas. We'll need that. So here's the data set. I don't have any labels here for the different features, but that's okay. I don't particularly care, actually, what these things mean anyway. As I was just describing, I don't really know what these things are. They don't particularly have meaning to me. I know what length and width mean, of course, but there's no, in my mind, significance about these quantities because I don't know anything about flowers. So let's just assume that we have kind of like a collection of measurements for a variety of objects. And then for labels, we have these numbers, and these correspond with the different species of iris. And again, they correspond with particular species, Setosa, versicolor, virginica. But I don't particularly care about any of that. You know, again, those names don't have any meaning to me. We'll come back to them later, because if we want to communicate what our results are, we'll want to use those names because they will have meaning to others. But at least right now, when my task is machine learning, and I am not an expert on the subject matter, it's not particularly important for me to know what these names are. So, charging on ahead, let's do some visualization to acquaint ourselves with the data. And I'm going to use the Seaborn library to make a grid of plots showing the distributions of the observations along pairs of different features. So if we look, for instance, at feature 3 versus feature 0, we see the distribution of points in that space. And if we, in particular, for example, look at feature 2 versus feature 0, we see kind of two clusters of points. A cluster down here and a large spread out cluster up here. So there is apparently some distinction being made between some of the flowers by a combination of feature 0 and feature 2. Feature 0 alone doesn't do it, because if we imagine looking only along this axis, some of the points in this cluster up here would collapse onto feature 0, and we would just see kind of a broad distribution across that. So that's actually shown in this histogram of feature 0, where we see just kind of our observations spread out over the axis. We don't see any particular groups or distinctions between, that seem to identify different clusters in this histogram. Feature 2 does have a bit of that. So if you imagine looking only at feature 2 and collapsing all the points onto this axis, there's a gap here, which we see reflected in the histogram. There's a gap. So feature 2 already seems to distinguish somehow between some group of flowers and another group of flowers. Likewise for feature 3. Feature 3 has a gap here, a gap here. No matter how what feature we plot with it, because it's a gap that exists purely in feature 3, there's kind of a group with a small measurement and a group with a larger measurement. So this is a very good sign. Already looking at single features, individual features, or combinations, pairs of features, we can easily imagine separating the flowers into two clusters. And if we're lucky, these two clusters will correspond with at least, two different species of iris. Maybe most of the Setosa are over here, most of the Virginica are over here, who knows? And one way to verify whether this separation actually is meaningful in terms of species is to add some color. So let's add color by setting the hue keyword equal to the labels. So that's not going to work. turn this into a series. Index equals df.index. Still not working right. Okay. Really? Buffer has wrong number of dimensions. Expected one got 2. Let's try this. For real? Oh, axis equals 1. There we go. Now, axis equals 1. There we go. Okay. So, nothing too interesting going on here. All I did was, and this just has to do with the peculiarities of this function, I tried to set the hue equal to just this array of labels. It didn't like that. I tried reshaping it to be a column vector. It still didn't like that. And finally what I had to do was make a data frame that contained the labels themselves, and then specify which column would be the label. I thought the pandas series would work on its own, but evidently not. I'm not sure why. Anyway, ignoring this column over here, label, which has kind of nothing to do with, this is not something we can use to make a prediction, right? It's the label itself, or this bottom row. Just focusing on this 4x4 grid, we see that the clusters we had seen before do indeed discriminate between species. So always this kind of cluster that sits off by itself is label 0. And then we have this larger cluster that has 2 species in it, but they're largely separated. Not always. Here they're pretty mixed together, but here they're largely separated. Here they're pretty separated. Here they're pretty separated. Which means we could probably still, even though the separation's not as good or clean as between blue and orange, or blue and the other species, we could still draw some kind of separator that would cut through the second cluster and divide the 2 species. And that's really what we're going to try and do with machine learning, is draw a line that separates these clusters. And that drawing a line amounts to a linear model. Only it's not going to be linear regression, it's going to be called logistic regression. And that will be the main subject of this lecture, is logistic regression. And just like linear regression is going to give us a baseline to consider many regression tasks, logistic regression is going to be our baseline for considering different classification tasks. We'll often be falling back on logistic regression, which, as we'll come to see, is actually based upon linear regression. So, let's have a look at how we use logistic regression, and then I'll talk about what it actually does. So, in scikit-learn, in the linear models module, we have a logistic regression estimator. I really hate that this is called regression. There's really no, it's a misnomer, really. So go ahead and make one of these objects. And just like basically any estimator in scikit-learn, we can fit that model to the data. So now we have a fitted model, and if we wanted to evaluate the model, you can see it's 96% accurate, meaning it correctly predicted the label for 96% of the observations. That's 144 of the observations. So it got 6 wrong out of 150. So what actually happened when we did this? And what do the results look like? So I am, let's see, how do I want to do this? Let's look at features 2 and 3 and see where let's actually only fit our model to features 2 and 3, and then we'll look at where the decision boundaries come up. So the decision boundary are the boundary lines that will dictate where we separate observations into separate categories. So if we only look at features 2 and 3, we'll look at the coefficients. Why do I have 3 here and not 2? Oh, right, one for each class. Of course, of course. So each class has an associated set of coefficients. So, let's see. Now, how do I get the boundaries? Oh, because this is a 3-category problem, this is going to be much more complex. Okay, so maybe I want to do this a somewhat different way. So I'm not going to do it analytically, I'm going to do it computationally. So what I'm going to do is create a grid of points and make predictions for each point in the grid, and then by plotting them we'll see the boundaries. So let's see, min or df2.min, df2.max. We'll take, let's say, 1,000 points, df3.min, df3.max, another 1,000 points. Actually going to import one more thing here. Just so I can get a handy progress bar. There we go. So let's see. 1,000 times 1,000 is 1,000,000. So we're about halfway there after 13 seconds. So this will just take shy of half a minute. Done. So how am I going to go about plotting this? predictions, where predictions 2 equals category. So we'll do it this way. We'll slice out the part of the array where we've predicted a particular category and plot that. So here we go. This is our decision boundary. And if we were to do the same thing, plotting instead of our predictions, the actual data, so if I remember, the first 150 or the first 50 are there's 50 of each category, so I can just increment by 50 to get each category. Okay, so the colors, do they match up? Yeah, they match up. So we see the decision boundary for blue cuts from down like this, cleanly separating off blue. And then orange kind of comes along this boundary, maybe like that. And then green is everything sort of above here. Maybe we can plot these together. Can I somehow provide alpha equals 0.5? So that didn't work great, but you can kind of get the idea. And the reason it's not working great is because I'm getting these overlaying colors. So yeah, it doesn't work great. And then, yeah, another reason is because this is like very hacky. This is like not the way to draw a background. But again, you can see kind of the one cluster separated off down here, and then this boundary tries to cut between the remaining 2 species of iris. So we have one boundary, and then another boundary. Now, of course, these boundaries could have been yeah. These boundaries are formed by the intersection of 3 different equations. And so it's not possible to have so there needs to be an intersection somewhere. We could imagine pulling this intersection off kind of in this direction, maybe, so that this boundary would instead cut through this way, and then another boundary cutting down here. And then maybe a third boundary cutting this way. But we do need to locate this intersection point somewhere. And the mathematics of how this works actually comes back to linear regression. So earlier I looked at the coefficient attribute of the model, and what we're seeing here is actually a linear model for 3 different categories. So we essentially have these 3 equations . These 3 different linear equations that essentially make some kind of like prediction for each point given its x2 and x3 values. So it predicts 3 different values which are proxies for the probability of belonging to one of the 3 classes. And whichever of these formulas gives the largest value is the whichever one gives the largest value is the predicted class. So each of these corresponds with a line. You might recognize these as the equations of lines in a 2-dimensional plane. And the way that we get from these to probabilities, right? These will be arbitrary numbers. X2 could be any number, and minus 1.14 times x2 could also be kind of any number from negative infinity to positive infinity. So the way we get to probabilities in the end is by applying what's called the sigmoidal function. The sigmoidal function has kind of this shape. This is too big. Where it smoothly goes from 0 to 1, and it plateaus both off to negative infinity and positive infinity. And this gives us a mapping from the outputs of each of these lines onto the numbers 0 to 1, probabilities. So we apply this sigmoid to the output of each of these equations, each of these equations of lines, and then we ensure that their sum comes up to 1, because the sum of the probabilities must be 1. It's either category 0 or category 1 or category 2. There's no leftover or excess probability. And if you're curious, the equation for that sigmoid function is here. 1 over 1 plus e to the minus t. This is also called the logistic function, hence logistic regression. So here's the standard logistic regression, which shows a little bit, shows it centered at 0. And it shows in a little bit more clearly that plateau as we head off to infinity in either direction. So for example, if I take the point x2 at, say, 3 and x3 at 1, not quite what I wanted. Nope. There we go. So here are the values given by the equation of these lines at this point 3, 1, about here. And we see the value, the largest value is this second category. In fact, if we predict we get back the second category, this one. And we could also define a sigmoid function for some number x, or let's say n. That just returns 1 over 1 plus the exponential of negative n. I believe that was the correct formula. Yes. So if we apply the sigmoid, there we go. So we get our probabilities of belonging to each class. Well, these aren't the probabilities quite yet, because let's see, I need to normalize them. So that they sum up to 1. And this is not pretty code. So here we have the probabilities. So we have a 41% chance that this belongs to category 2, 35% chance that it belongs to category 1, and a 25% chance that it belongs to category 3. Which makes sense. This is very close to the boundary of all 3. So we expect the probabilities to be fairly even between all the classes. But it does lie inside the decision boundary for the second class, which we see has the maximal probability. So we'll look at the time here. Okay. So logistic regression is essentially the same as linear regression. You know, I fit a linear model that then has this sigmoid or logistic function applied on top to convert the output of our linear model to probabilities. And what I'm trying to do is to optimize those outputs so that the selected class matches the ground truth. So this is a case where we commonly use gradient descent. The mathematics for trying to optimize the model parameters is a little bit complicated. The gist of it is you can compute the expression for the maximum likelihood in terms of the model parameters, and then once you have that expression for the maximum likelihood in terms of the model parameters, you can use that as a sort of objective function to be optimized by gradient descent. So there's not an analytical solution for what these coefficients should be, unlike in ordinary least squares linear regression. But we can use gradient descent to fit these logistic regression models. As we discuss more complex classifiers, will no longer be restricted to linear decision boundaries. So the kind of hallmark of logistic regression is having linear decision boundaries, and that comes out of this connection to linear regression. You know, essentially all logistic regression is equations for a bunch of planes or lines, linear shapes, with logistic functions applied on top. So we're just drawing linear separators between different classes in our feature space. So, not a lot more to say about classification at the moment. I mostly just wanted to introduce logistic regression and also introduce this idea of predicting categorical labels where, 2 is not more different from 0 than 1. 0, 1, and 2 are categorical labels. Taking a difference of 2 minus 0 or 2 minus 1 is not really sensible. And there's a lot of problems in machine learning that are classification problems. We'll be seeing them crop up again as we proceed through the lectures. And I will join you for the next lecture on metrics, where we'll discuss in more depth some examples of classification and how we determine whether or not we have a good classification model or not. Thanks for listening.